Okay, so today we'll be going over polynomials. We'll do an overview of polynomials in general, and then we'll focus more on univariate polynomials, talking about evaluation and interpolation. So, to start, we'll define a monomial. So, a polynomial is basically just the sum of multiple monomials. And a monomial itself is the product of a number and a set of variables. So variables could have exponents, but the exponents must be positive whole numbers. In this case now, let's say a, there is no number, but then there is a variable. So this counts as a monomial. 5a squared, the number is 5, the variable is a, and this a has an exponent of 2. And in this case is a cube b squared and then yt. So these are examples of monomials, and for non-monomials, you look at this. So b now has like a power of -2, and you are not supposed to have negative exponents. So this doesn't count as a monomial. This is made up of two monomials. So technically it's not a monomial, it's more of like a polynomial. Because we have 3a plus 2b. So individually they are monomials. So 3a is a monomial and 2b is a monomial, but because of they are grouped together via this plus, then it's not a monomial. And in that case, square root of 3p can be reduced to square root of 3 times p raised to the power of 1 over 2. 1 over 2 is not a positive whole number, so this is also not a monomial. So given a monomial, you can determine the degree. So the degree of a monomial is basically the sum of the exponents. So you sum the exponents for every single variable in the monomial. So in this case now there's just one variable, which is a, with an exponent of 1, hence the degree is just 1. In this case there's also just one variable, but with an exponent of 2, and that's why the degree is 2. In this case there are two variables with exponents of 3 and 2 respectively, so the degree is going to be the sum. That's 3 plus 2, which is equal to 5. And here we have a raised to the power of 3, b raised to the power of 1, and c raised to the power of 4. So the degree of this is going to be 3 plus 1 plus 4, which is equal to 8. So this is how you compute the degree of a monomial, and a monomial is going to serve as the basis for the creation of polynomials. Now there are different types of monomials. So we have the univariate monomial and we have the multivariate monomial. Now this specifically is talking about the number of variables in the monomial. So univariate just means one variable monomial. And in this case, you can see that each of them have just one variable. So this one has just an a, this one also has just an a, this one has an x, and this one has just y. So this is a univariate monomial. Then we have multivariate monomials. Multivariate monomials are monomials that have multiple variables in them. So this has a and b, this one has x, y, and z. So this is multivariate monomials. So the degree of this is going to be 3 plus 2, which is 5, and the degree of this is going to be 16 plus 8 plus 5, which is 29. Okay. Now let's look at polynomials. So polynomials are basically made up of monomials. So basically you have a monomial and then you sum different monomials. So you have one monomial, in which case that's just a monomial. Like I have a polynomial that's made up of just one monomial. So a monomial is basically a polynomial, but a polynomial is not always a monomial. But you can also have let's say 2. So this is a monomial and this is also a monomial separated by a sum. And you can have 3 or as many as you want. So a polynomial is just the sum of multiple monomials. And there are also very specific, there are some specific definitions that in case you want to communicate more context about like the polynomial you're describing. So if your polynomial has just one term, you can just call it a monomial. If it has 2 terms, you can call it a binomial. If it has 3 terms, you can call it a trinomial. Now we go to the degree. So the degree of a polynomial is basically the highest monomial degree. What this means is that you need to look at each monomial in the polynomial and check for the one that has the highest. So whatever the highest degree monomial is, the polynomial would inherit that degree. And we'll look at some examples now. So this is an example: 3x raised to the power 4, x raised to the power 3, 4x squared, x, and 5. So what we need to do is we need to compute the degree of each term here. So in this case, this is 4, this is 3, this is 2, this is 1, and this is 0, right? Because this is like 5x raised to the power of 0. So when you look at everything, you realize that the highest degree monomial is this one, which is 4. And that will basically be the degree of the polynomial itself. So the degree of the polynomial is basically 4. Now, depending on the type of monomial that a polynomial is built up from, that will also determine the type of polynomial that we're going to be working with. So if a polynomial is built up from, let's say, like univariate monomials, and all the univariate monomials have exactly the same variable, then that is called a univariate polynomial. So in this case, we have 4 monomials. All of them have just one variable, so that's a. This 8 can be seen as 8a raised to the power of 0, and they're all built up of a's. So this is technically a univariate polynomial, and you can notice this from the function signature, which basically says that I just have one variable, which is f of a. And the degree computation is exactly the same thing, right? So you pick the highest, which is this a raised to the power of 3. So the degree of this polynomial, this univariate polynomial, is 3. Now, a multivariate polynomial is basically a polynomial that is made up of monomials that have more than one variable. Made up of monomials that have more than one variable. In this case, basically like the polynomial itself has more than one variable. That's like the simplest definition. In this case here, you have x and y. So you have x squared y cubed, 2 variables. So just by looking at the function signature, you can tell whether it's a univariate or multivariate. In this case, it's x, y, z, x, y, z. So multivariate. Now we can compute the degree. The degree is still the same. So in this case now, this is 2 plus 3, which is 5. So that's the degree of this. In this case, we have 2 terms. So this is 1 plus 2, which is 3. And this one is 1 plus 1, which is 2. And we pick the highest, which is 3. So the degree of this polynomial is 3. In this case, we have 4, then 2 plus 2 is 4, and 4. So everything is 4, the highest is still 4. So the degree of this is going to be 4. And that's how you compute like the degree of a multivariate polynomial. So I'm also going to be sending this resource. So this is going to be available to go over. Then a multilinear poly is a specific type of a multivariate polynomial in the sense that it still has multiple variables, but every variable has maximum exponent of 1, right? So you're not going to see any variable that has an exponent of 2, 3, or anything above that. So the maximum you're going to see is 1, and you can also see 0. So that means that you can have a constant. So technically, you should be able to have something like 3xy plus 2y plus 5. But because this 5 is technically like, you can think of it as a variable raised to the power of 0. So it still fits the constraint that no power must be greater than 1. So this is 3x, x just 1, y just 1, z just 1. And the degree computation is still the same. So this is just 1, this is also just 1, this is also just 1. So the degree of this entire thing is just 1, right? And then you have 3xy plus 2y. So this is x has the power of 1, y has the power of 1, and this y also has the power of 1. So it is multilinear. The degree is going to be 1 plus 1, which is 2, and then 1. What's the highest one? That's 2. So the degree of this multilinear polynomial is 2. So those are basically the different types of polynomials and the way you can compute the degree, starting from monomials and building all the way to polynomials. Now we are going to focus more on just the univariate polynomial, which are polynomials of this form that have like one variable and arbitrary powers. So we care about 2 things. We care about evaluation and interpolation. Let me get my icon. Okay. So first, we're going to look at evaluation. So you have some polynomial or some univariate polynomial definition, which for example could be f of x is equal to 2x squared plus 3x plus 5. And the goal is basically to evaluate this polynomial at any point of x. So we could say x is equal to 3, right? And evaluation is basically just a rewrite. So you're going to replace everywhere you say x with the concrete value, which in this case is going to be 3. So f of 3 is basically 2 into 3 squared instead of x squared plus 3 into 3 plus 5 is equal to 2 times 9 plus 9 plus 5, which is equal to 18 plus 9 plus 5, which is equal to, this should be 27, right? 27 plus 5, which should be equal to, I believe, 32. Yes. So this is how you do evaluation. It's very straightforward. Just replace the variable with the concrete value and simplify to the lowest form. So this is not particularly interesting. What we care more about is interpolation. So to define interpolation, I first of all need to define a fact. And the fact is that every degree D polynomial, so you can write, basically there are two ways to represent. Okay, I'm going to show two ways to represent polynomials, there may be more than that. So you can take a polynomial written in coefficient form. So what I've been writing has been polynomials expressed in coefficient form. So 2x squared plus 3x plus 5 is coefficient form because of this 2 here is the coefficient, this 3 here is the coefficient, and this 5 here is the coefficient of this x raised to the power of 0. So we have coefficients for different powers of x. That's the essential idea. But there are other ways that you can write polynomials of this one. So there's something called the evaluation form, which is basically, rather than expressing the polynomial as an equation or in this form, you instead pick points that exist on that polynomial, and that is basically going to be your representation. So the question now is like, how many points should you pick? There's this fact that basically says that for every degree D polynomial, you need at least D plus 1 points to equivalently represent it. So what this means is that if you have a polynomial that is, let's say, a degree 2 polynomial, we have a degree 1 polynomial, for example. So let's say f of x was equal to 2x. The degree of this polynomial is 1. So this means that we can write it this way, 2x, which is coefficient form, but we can also write it in evaluation form, which is basically saying pick a set of points on this polynomial, and then that will be your representation. So since the degree is 1, we only need D plus 1 points, which is 1 plus 1, which is 2. So that means that with just 2 points, we can uniquely represent this polynomial. Let me just pick arbitrary points. Let me pick f of 0. So I'm going to evaluate this polynomial at 0, which is going to be 2 times 0, which is equal to 0. And I'm going to do f of 1, which is basically 2 times 1, which is 2. So I have 2 points now. I have 0, 0, and 1, 2. Now with these 2 points, I have uniquely described this polynomial on the other side. So what I'm saying now is that 2x is equivalent to 0, 0, and 1, 2. Meaning that given this, I can go this way, which is what we did here with the evaluation. But then also, given this, I can go this way. And this is what we're trying to learn, which is interpolation. So given the evaluations, as long as the evaluations are D plus 1, and they all lie on this polynomial, then we can always go back to that polynomial using polynomial interpolation. So let me just show an example of this in action. So we can use decimals to print, to draw the graph. So I have 2x, that's the graph. So this is the line here representing 2x. Now I pick 2 points on this graph. So I picked 0, 0, which is this point here, and I also picked 1, 2, which is this point here. So you can see that both points are on this line. What this means is that I could get those points from the line by just evaluating it at 0 and evaluating it at 1, but also I could retrieve or recover the line back by just drawing these 2 points and then using like a ruler or something to draw a straight line that passes through both points. So once I draw a straight line that passes through both points, that straight line will be exactly equal to the 2x. So this is how you can go forward and backward. And we're going to show exactly how you do this mathematically using a technique called Lagrange interpolation. Okay, so let's use something bigger. So let's assume we have let's use a quadratic curve. Let's say 2x squared plus 3x. Right, so this is there's a curve like this now. So we can represent this using just 3 points. You know, the degree of this is 2, and we can write this way. This is the coefficient from representation, but we can also write it by picking just 3 points on this curve. Any 3 points, as long as the 3 points fall on this curve, it's exactly equivalent to this. So let's compute this. Two x squared plus 3x. If we evaluate this at also evaluate this at 0, f of 0. F of 0 is going to be 0, right? Because 2 times 0 plus 3 times 0. That was the f of 1. F of 1 is going to be 2 times 1 squared plus 3 times 1, which is equal to 2 plus 3, which is equal to 5. And then f of 2 is going to be equal to 2 times 2 squared plus 3 times 2, which is basically equal to 2 times 4 plus 3 times 2, which is equal to 8 plus 6, which is equal to 14, I believe. So given these 3 points, I can get back the original curve, which is 2x squared plus 3x. So what are the 3 points? The 3 points are basically 0, 0, 0, then 1, 5, and 2, 14. Right? So let's check if these points are actually on the graph. So 0, 0 is here, which is on the curve. Then we have 1, 5, which is here on the curve, and then we have 2, 14, which should be somewhere here. Yeah, so that's it. So the 3 points are here. Now there's only, so given 3 points, we can reconstruct the curve by just like fitting a line through this, and since it's going to be a quadratic curve, it's always going to be unique, like d plus 1 points. So one thing I can show is, before looking at how to do interpolation ourselves, we can use a calculator to do the interpolation. So let's say interpolate 0, 0, 0, 1, 5, and 2, 14. If we interpolate this, we get 2x squared plus 3x, which is exactly what our original polynomial was. But then there's no reason why it has to be just this. Like I could pick another point here. So let's say I evaluate it at minus, let's say at -1. Let me do this on the iPad. So f of -1, that's going to be 2 into -1 squared plus 3 into -1. Right, so that's going to be 2 into 1, so this is just 2, and -3, which is equal to -1. So f of minus 1 is basically equal to minus 1. This means that there's an additional point that exists on the graph, which is like minus 1 is equal to minus 1. And this can be added to our interpolating set. We said it needs at least d plus 1 point. So this means that even if we do more than d plus 1 point, it will still give us the same curve. So let's say minus 1 from minus 1. We should still get the 2x squared plus 3x, which is what we have here. Because the points all lie on the same point, and interpolation is just finding the polynomial that passes through all of them. But then we added redundancy. So technically we could remove any one of these points and still have the same polynomial 2x squared plus 3x. So let's say we removed 1, 5, for example, and we interpolate, we still have 2x squared plus 3x. So any 3 points on the curve is sufficient to properly describe it. And but once you now do less than that, so let's say we remove this, then we can't get the same curve again because we have lost information. We're not providing enough information to completely describe it. Okay. So now we are going to look at a way to do this interpolation by hand, which we call the Lagrange Lagrange interpolation. So there are multiple ways to do this, but I'm going to use Lagrange interpolation for now. There's FFT and entities, which are a way to like convert a polynomial from correction form to evaluation form in a much faster. So like Lagrange interpolation runs in O of n squared, while FFT runs in O of n log n. And I really encourage people to like look into FFTs, try and understand it and implement it. We'll still teach it just before starting polynomial complement schemes, but it's encouraged to look at it yourself and implement it and let us know if you face any issues. So let's look at the Lagrange interpolation. So the goal of Lagrange interpolation, or the goal is basically like given a set of points. So let's say this point here, 0, 0, 1, 5, 2, 4, 0, 0, 1, 5, 2, 14, I think. Yes. So we want to take this in, and then at the end of the day, we want to spit out 2x squared plus 3x, right? So that is the goal. That's the goal. So what does this mean? It means that we're trying to find a function f that if you evaluate it at 0, you're going to get 0. That's based on this. If you also evaluate this function at 1, you're going to get 5. That's based on this. And if you evaluate it at 2, you're going to get 14. That's based on this. So this is the behavior that we want our function f, this function that we're looking for, to have, right? So how can we do this? Now let's imagine we had this structure. So say f of x is equal to, now these are the outputs that we're expecting, right? 0, 5, and 14. So we should get 0 when we multiply. So I'm just going to write something out. Then we should get 5 for the next output. And we should get 14 for the next output. Okay? I hope this makes sense. So, what's the idea of these L functions? Right now, I've not defined what they're supposed to do, but just looking at the behavior that we are trying to achieve, we can figure out how this should behave. So, when you do f of 0, we're expecting 0. Okay, this is actually a bad example. Let's use f of 1. Let's use f of 1. So when you do f of 1, we're expecting 5. Now 5 is right here, right? So if 5 is right here, how can we set the values for L0, L1, L2, such that when we sum up everything, we'll get 5? So the way to do that is, you want L0 to collapse to a 0, right? So it's going to be 0 times 0. Then plus 5 times. You want L1 to collapse down to a 1. And you want L2 to collapse down to a 0. So the terms that you don't need, you zero them out. And the term that you need, you collapse the L value to a 1. We'll go into more details as to how this can be achieved, but this works, right? Because this is like 0 plus 5 plus 0, which is basically equal to 5, which is what we want. Now, what of f of 2? If you wanted to do f of 2, L0 should be 0, L1 should be 0. No. Yes, because we're trying to get the output of 14. But L2 should be 1. So we want to be 0 times 0 plus 5 times 0 plus 14 times 1. And that's basically 0 plus 0 plus 14, which is equal to 14. Now, let's go back to f of 0. So for f of 0, we want this to be selected. So this is going to be 0 times 1. Now L0 is going to be it's going to turn to 1, while the rest of them should turn to 0, right? That's the idea. And if we somehow achieve this, this is going to be 0 plus 0 plus 0, which is equal to 0. So Lagrange interpolation is basically the multiplication of each output with a Lagrange basis polynomial. And these polynomials act as selectors. So depending on which one is on, you can kind of like select a specific output. So you have all your outputs. So you have 0, which is an output. You have L0 of x. You have 1. No, there's not 1. I think it was 2. No, 5. You have 5, which is another output, L1 of x. And you have 14, which is another output, times L2 times L2 of x. So this is the goal. And this L function should be able as selectors. So if x is 0, then this should turn to a 1. But if x is 1 or 2, then this should turn to 0, right? So I wrote it conveniently that this subscript here, 0, is what this function is looking for, this particular one here. So this particular L function is looking for a 0, right? So if you look at the interpolating set is basically the x values for all the points that we're interpolating. So in our case, the interpolating set is just 0, 1, and 2. Or it could be any value. So as long as, it depends on where you evaluated at, right? So if we had used these 3 points, right, we also remove the 0, 0. So we had used like 1, 5. So we use minus 1, minus 1, and we use 2, 14. Then the interpolating set will be 1, which is this, minus 1, which is this, and 2. That will be the interpolating set. Okay, cool. So, the idea of these functions is that this L0 is saying that, okay, if I see a 0, I'm going to turn myself into a 1. But if I see any other thing in the interpolating set that is not 0, I'm going to turn myself to 0. So in our case, the interpolating set is what? 0, 1, and 2. So now let's look at the behavior of L0 of x. So L0 of x, if it sees 0, if x is equal to 0, then it's going to output 1. But if it sees 1, it's going to output 0. And if it sees 2, it's also going to output 0. That's the behavior. Then let's look at L1 of x. L1 of x, if it sees 0, it's going to output 0, because that's not what it is looking for. It's looking for a 1. If it sees 1, it's going to output 1, and if it says 2, it's going to output 0. So the output is always like 0 or 1 when you evaluate it with any value in the interpolating set. Now let's see L2 of x. L2 of x, if it sees a 0, it's going to output a 0. If it sees a 1, it's going to output a 0. And if it sees a 2, it's going to output a 1, because 2 is what it was looking for. So this is how the L functions are supposed to behave. So we need to figure out how to encode this algebraically, right? So one idea is, okay, how can you get a 1, right? So to get a 1, you could do something, let's just call it A, over itself, right? That's going to give you a 1. So anything divided by itself is going to be a 1, and except for 0 over 0, but any natural number divided by itself, that's not 0, it's going to be a 1. But you can also do 0 over A. So now, once there's 0 at the top, regardless of what the bottom is, it's always going to be a 0. So with these two structures, we should be able to create these L functions. So let's focus on this L0 of x. L0 of x. Assuming that the interpolating set is 0, 1. 0, 1, and 2. So the question now is like, how can we construct an equation such that if you evaluate that equation at 1 or 2, we're going to have 0. But if we evaluate it at 0, we're going to have 1. So that's the question. So the question now is, okay, since we want 1 and 2 to evaluate to 0, that means that the top has to somehow evaluate to 0 if there's a 1 or there is a 2. And how can you make something evaluate to 0 if you see? So let's say we wanted some expression to evaluate to 0 if it sees a 1. The easiest way to do that is just subtract 1 from that thing, right? Because if we replace a 1 here, it's now be 1 minus 1, which is going to be equal to 0. So what we could do is that we could have expressions like this that cancel out a particular number, and we could put them at the numerator for all the things we want to cancel out. So since we want to cancel out 1 and 2, then we should do x minus 1 times x minus 2. Now, if we have a 1, this node here is going to be 0, and then this doesn't matter. The entire output of the numerator is going to be 0. If we have a 2, then this other node here is going to be 0, and this doesn't matter. The entire output is going to be 0. So essentially, we have created a numerator such that if x is 1 or x is 2, the top is going to be 0. And then it doesn't matter what we divide by, the answer is going to be 0. So right now, this alone is already sufficient for evaluating to 0 when we see a 1 and evaluating to 0 when we see a 2, which is the case that we had here, right? Now, the only thing we haven't seen is that, okay, what happens when we evaluate to a 0? So now, there's a reason why we cannot put x minus 0 at the top, right? Because if we put x minus 0 at the top, then when we see a 0, it will also evaluate to 0, right? Because this will be 0 times 0, which will be 0, and it won't matter what is there because of the product. So everything will just be 0. Hence, we can't put x minus 0 there. So, but once it's evaluated to 1. So what happens when we evaluate at 0? If we evaluate at 0, the top is going to turn into what? 0 minus 1, right? And then 0 minus 2. So now we know what it will look like when we evaluate at 0. Hence, we can just divide by that. So now, this is the L0 of x function. This is the function that, given 0, is going to evaluate to 1, and given 1 or 2, is going to evaluate to 0. Which should be easy to see, right? Because if evaluate is at 1, then that will be 1 minus 1 times 1 minus 2 divided by 0 minus 1 and 0 minus 2. But this 1 minus 1 is going to turn into a 0, right? So this is going to be 0 times 1 minus 2. So everything at the top is going to turn into a 0. And then it doesn't matter what's at the bottom. And 0 divided by anything is still 0. So at the end of the day, it becomes 0. And the following argument is also sufficient for showing that 2 would make it collapse down to 0. So then the interesting thing is now, okay, what happens when we evaluate at 0? So when we evaluate at 0, we are replacing x with 0. So that's 0 minus 1, 0 minus 2. But still, it is exactly equal to the denominator. And since it's exactly equal to the denominator, we're in this case where a divided by a is equal to 1, and then we get 1. So this is how we're able to get 1 for 0, and then 0 for the rest. So this is how you compute the L functions. Now let's compute the L function for 1. So let's say we're looking for 1, but if we see 0 or 2, it should disappear. So this means that we do x minus what? X minus 0, because if we see 0, we want the top to be 0. And we also do x minus 2, because if we see 2, we want the top to be 0. But then we now say, okay, we can't put x minus 1 at the top because we're actually looking for 1. So we just imagine the numerator when we evaluate at 1 and just write it down. So that's going to be 1 minus 0 and 1 minus 2. So this is a function that given 1 is evaluate to 1, but given 0 or 2 is evaluate to 0. Now let's do for L2 of x. So we're selecting 2, meaning that we want to collapse down to 0 if x is 0 or 1. So this is going to be x minus 0, x minus 1, not x minus 2, because of that will collapse 2 also. But then we divide it by what it would look like when we evaluate it at 2. So this is how you construct the L functions. So once you have constructed the L functions, all you need to do is just replace them back in here and then simplify. Once you simplify, you're going to get back the original polynomial that created that gave you the point evaluations. So we're just going to go through 2 examples just to make things a bit clearer. Now let's imagine we had a polynomial f of x, which is basically equal to 3x plus 5. Okay, now this is a degree 1 polynomial, right? Because the highest monomial power of x is 1. And that means that if we want to express this in evaluation form, we would need d plus 1 points, right? Which is basically 2 points. So we need 2 points. 2 points. So we can pick any arbitrary 2 points, right? We could evaluate at 0 and 1, but let me just evaluate at some random points. So let me evaluate at 2 and 4, for example. So f of 2 is equal to 3 in 2 plus 5, which is equal to 6 plus 5, which is equal to 11. And then f of 4 is equal to 3 in 4 plus 5, which is equal to 12 plus 5, which is equal to 17. So we have our 2 points. We have 2, 11, and then we have 4, 17. So since these 2 points fall on this line, and we needed 2 points to uniquely describe the line, then that means that this is another way of writing this. So now imagine we don't know this, but we know this. How can we go back? This is where the Lagrange interpolation comes in. So we want to construct a new function called f of x. So now f of x is supposed to output 11 when it sees 2. So that means we need a selector for 2. So we'll create an L function that looks for 2. And then we add that to the next output is supposed to be 17. And 17 comes when you select for 4. So select for 4. So once we can construct these 2 L functions, one that selects for 2, so meaning that if this gets f of 2, it will turn into a 1, so it will be 11 times 1, which will be 11. And then this other one, since it was not looking for 2, it will turn into a 0, so this entire place will turn into a 0. Hence, the output when you evaluate at 2 is going to be 11, which is what we want. But also, if we evaluate at 4, this was not looking for 4, so this will evaluate to 0, which will remove 11. But this was looking for 4, so this would evaluate to 4 to 1, sorry. Then 17 times 1 is 17, which is exactly what we're looking for. So once we have this L function that behaves in this way, then we can recover the original polynomial. So the question now is like, let's beat the L function. So our interpolating set is basically the x values. So that's 2 and 4. So interpolating set is basically 2 and 4, meaning that we are looking for one of these, but then we need the rest of them to become 0. So let's work on L2. So L2 of x is saying that if I see a 2, I want to keep it at, right? I'm looking for a 2, so I don't want it to turn to a 0. But if I say a 4 or any other thing in interpolating set, I want that to be a 0. The only other thing in interpolating set is 4. So that means that the only thing that we're trying to kill is basically 4. So this is basically x minus 4. So if there's a 4, then the top is going to be 0, which cancels out everything. But then we now need to assume, okay, what happens if it's not a 4? What if it's a 2 that we're actually looking for? Then we just duplicate what that would look like at the bottom. So if it's a 2, then it's just going to be 2 minus 4. So that way, if you put a 2, then the top is going to be equal to the bottom and everything is going to be evaluated to 0. Now let's simplify a bit. So this is x minus 4 divided by minus 2, and this is basically 4 minus x over 2. I just took the negative sign up. So this is L2 of x. Now let's compute L4 of x. So L4 of x is basically equal to, so now we don't want to see a 2. So if there's a 2, if a 2 exists, we want that to be destroyed. So that's x minus 2. Then we divide that by what happens when there's a 4. So that's basically 4 minus 2. So this is basically equal to x minus 2 divided by 2, which is equal to, okay, that's the simplest form. So now we have the L2 and we have the L4. So what we need to do is come back to this function here, or this expression here, and replace L2 with the concrete value and also replace L4 with the concrete value. So f of x is going to be equal to 11 times 4 minus x over 2. And the other one is going to be 17 times x minus 2 over 2. So what we could do is we could now distribute the 11 in. So that's going to be 44 minus 11x over 2 plus 17x minus 36, I believe. 36 is 34. 34. 4 all over 2. Then we can just add everything up. So that's 44 minus 11x plus 17x minus 34. I hope this is correct. I don't know. So 44 minus 34, that's 10, right? Then 11x, 17 minus 11, that's 6, right? So that's plus 6x, all divided by 2. So when you divide both sides by 2, that's going to be 3x plus 5, which is the original polynomial that we had to start with. 3x plus 5. So this shows you that you can use interpolation to, given just the points that's given this, so this was not known, we're able to recover the original thing by using Lagrange interpolation. So we're going to do one more example using a more a quadratic polynomial, so like degree equals 2. So that's what we had, 2x squared plus 5, no, plus, let's say plus 8. 2x squared plus 8. Now this is a degree 2 polynomial. So if we wanted to represent it as a set of evaluation points, we would need d plus 1, right, which is going to be 2 plus 1, which is 3. So we need 3 points. 3 points to represent this in evaluation form. The 3 points are basically going to be, you can just pick any random point. So now I'm going to go back to 0, 1, 2 just because of I prefer that. But it could literally, like as was shown here, you could literally use any value for x. Okay, so if our value is at 0, so f of 0 is going to be 8, f of 1 is going to be 10, and f of 2 is going to be, so that'll be 2 times 2 squared plus 8, which is equal to 2 times 4 plus 8, which is going to be 8 plus 8, which is going to be 16. All right? Yeah. So this means that we have the following points: 0 to 8, 1 to 10, and 2 to 16. And now, since like why I like using 0, 1, 2 as my interpolation sets and above is basically because that's I can reduce the evaluation to just a vector of the output, since I implicitly know that the index 0 of this array corresponds to the x value, index 1 corresponds, and index 2 corresponds, then I can represent this same thing more succinctly. And that's why I prefer using just like a predefined interpolation set. Okay, cool. So we don't know this. We forget about this, and then this is all we are given. Now we need to compute we need to get this back, but just using this. So we know that our function is invariant, so that's f of x. So f of x is going to be equal to um, the output 8 times something that is selecting for 0, then plus the output 10 times something that is selecting for 1, plus the output 16 times something that is selecting for 2. So firstly, we'll build the Lagrange basis functions, and then we'll come back and insert them, then simplify, and hopefully we get back to x squared plus 8. So let's start with L0 of x. The interpolating set, don't forget, is just 0, 1, and 2. So we're selecting for 0, meaning that we want 1 and 2 to cause it to become 0. So we do x minus 1, x minus 2. Then we now assume, okay, what happens when we evaluate at 0? That's basically going to be 0 minus 1 and 0 minus 2. So if we simplify this, we can do x squared minus 2x minus x plus 2 divided by 0 minus 1 is minus 1, 0 minus 2 is minus 2, so at the end of the day, the entire thing is 2. And then we can simplify this further, minus 3x plus 2 all over 2. So this is the L0 of x polynomial. Now we compute the L1 of x. Now we're selecting for 1. This is going to be x minus 0, which is the same thing as just writing x. Okay, I'm just writing full. But now we're not selecting, well, since we're selecting for 1, it doesn't make sense to put it at the top. So this is going to be x minus 2. Then we're going to divide it by, imagine we evaluated at 1. So this is going to be 1 minus 0, 1 minus 2. Now we simplify this a bit. So this is going to be x times x minus 2 divided by 1 minus 0 is 1. 1 minus 2 is minus 1. 1 times minus 1 is minus 1. And then when we simplify the top, that's x squared minus 2x divided by minus 1, meaning that we can flip it. So 2x minus x squared. So that's the L1 of x. Now L2 of x. The L2 of x is x minus 0, x minus 1. Then imagine you evaluate at 2. So that's 2 minus 0, 2 minus 1. So this is going to be equal to x squared minus x divided by 2 minus 0, that's 2, 2 minus 1, that's 1, that's 2. So these are our L functions, L0, L1, L2. What we need to do now is insert it back into the original equation. So 8 times L0, which is basically 8 times x squared minus 3x plus 2 divided by 2. So technically this will cancel out and give you 4. Then plus 10 times 2x minus x squared, then plus 16 times x squared minus x over 2, which will cancel out and give you 8. So this is what we have. Now we can expand, right? So this is 4x squared minus 12x plus 8, then plus 20x minus 10x squared, then plus 8x squared minus 8x. So now we can simplify. So I'll gather like terms. I'll gather the x squares first. So 4x squared minus 10x squared plus 8x squared. That cancels out the square terms. Then minus 12x plus 20x minus 8x. Then plus 8. Right? Now we can simplify further. 4 minus 10, that's minus 6. Minus 6 plus 8, that's 2. That's 2x squared. Then minus 12 plus 20, that's 8. 8 minus 8, that's 0. Then we have plus 8 left. So this is our interpolated function. F of x is equal to 2x squared plus 8, which is basically what we have here. So that's invariant polynomial interpolation using Lagrange, the Lagrange interpolation method. There's another way to achieve interpolation and mass and bulk evaluation or batch evaluation, and that's using FFTs and IFFTs. We'll go into that in the future, but I advise that one looks into this on their own and see if one can implement this. Okay.